Hello and welcome back to our lab on architecture and networks. Today we will go to lab 1. We concentrate into LACVH, the instruction set architecture for ARM core. Here's outline of our experiments. Today we will concentrate on decoding machine language, or in other words it is reverse engineer. We will work with communication with people also. And about the reference, again we refer to two documents. Our lectures will appear like this, and our LACVH reference appear like this. Here is a reminder about what we did last time, and this table comes from LACVH. The core instruction formats. You can see that we have a number of instruction formats. All of them have the same length. For 32 bits come from 0 to bit 31, but they have different length in opcode, RM, RN, RG, and so on. We will concentrate into three formats that we already learned in your lectures and we already tried last time. Last lab 0. The first instruction is R format. It has 11 bits for opcodes, 5 bits for RM, 6 bits for RN, and 5 bits for RD. Two examples of R format can be seen here: H, RD, RN, RM, in which RD will be replaced by the value of RN plus RM. ER or exclusive OR, RD, RN, RM. In this instruction, RN will be exclusive OR with RM and the value will be written into register RD. A second format, I format, or work with immediate value. The opcode is 10 bits, the immediate value is 12 bits, and then RN 5 bits, RD 5 bits. Example can be seen here: HI, RD, RN, RM, RD, RN, and immediate. And HI means add with immediate. In this instruction, RN will be added together with immediate value here and written into register RD. The last format that we will think about in today's work will be D format. This will work with memory. It has 11 bits of opcode, 9 bits of offset address, 5 bits for RN, and 5 bits for RT. Two examples are shown here. Load and store. LDUR or load from memory, RT, RN, and then address. The value in memory at the offset address from RN will be load and written into register RT. For the store instruction, STURB, the value in RT will be stored in the memory to the offset address of address written here, and all this value in the format. Well, now we will go to first part of our lab today, decoding machine language. The situation is the Cyber and Government Security Directorate, CGSD of the Ministry of Defense, has interpreted a snippet of machine language in the iPhone 8 of a suspect who is planning a cyber attack on Black Friday. And your task is, can you provide information on the architecture of the processor, the assembly language code equivalent to the machine language, and you have to explain the assembly language code that you give from the machine language, and this will be the machine language that you received. Everybody can see that it is a number of 1 and 0, but we need to understand what does it mean for this code. Well, now we need to go to answer the first question, the architecture of the processor. In order to answer this question about the architecture of the processors, we will need to search what is the processor used in the iPhone 8. So we just simply use any search engine and we search iPhone 8 processor here. Well, and we can see the answer available here. It is Apple A11 Bionic, and it is a 64-bit ARM-based system on a chip. Well, so we have the answer for the first question of architecture of the processor here. It is Apple A11 and it is ARM core. And so we know from our lecture that ARM core use the lag V8 instruction as an instruction set. So it is a lag V8 instruction set architecture. So now we will need to we will need to find the assembly language code equivalent to the machine language. Here is the machine language. We will copy all those machine language and paste into any editor you have. Here I use Notepad, just a simple Notepad or anything you have. If you look into the this reminder or into lag V8 documents, you can see all the instructions, even regardless their format, they has 32 bits numbered from 0 to 31, and so all instruction will be 32 bits. You have to cut this binary sequence into a number of 32 bits. So here I will try to cut it. Well, from here to here should be 32 bits. We will check it now. Here is a 4, another 4, another 4, 4. Well, here you can see that it has 8 groups of 4 bits. 1, 2, 3, 4, 5, 6, 7, 8. 8 groups of 4 bits. And so from here to here you have 32 bits, and it will be one instructions in lag V8. We need to cut the instruction. We need to cut the bit sequence into all the sequence into a number of 32 bits like this. Yeah, I already do it before, and so I will just simply copy the result, and I will give you the result here. If you look into this, you can see that you will have 40 lines of 32 bits from line 3 to line 42, and each of this line will be one instruction in lag V8. Next, we will need to answer the question, what are the representatives of these for each of these 32 bits sequence in lag V8 assembly language. So in order to do so, we will look into our lag V8 reference data. Here you can see that we have the opcode for a number of instructions in LACVS. The opcode should have the size from 6, 8, 11, 10 or 9, and we will try to check the first instruction. This instruction first, it will start by 1 0 0 1 and then 3 other 0 and then 1 0 0. So we try to find all instructions start by 1 0 0 and 1. Here you can see 1 0 0 and 1 should start from here, and then 3 0 and then 1 0 0. So you can see it should be this instruction 1 0 0 1 and then 3 0 and 1 0 0. So we can see it is I format. The instruction is HI and it has 10 bits of opcode, 10 bits of opcodes. So with those research, we can write here, this one is HI instruction. Okay, and we need to cut it into, and well, now we back to our reminder. We can see here for I format, the operation working with immediate operands. We have 10 bits of code, 12 bits of immediate value, 5 bits for Rn and 5 bits for Rd, and we will need to cut it into 10, 12, 5 and 5. So here will be 10, 1 2 3 4 5 6 7 8 9 10, and next 1 2 3 4 5 6 7 8 9 10 11 12, and then 5 and 5. And the format for 8 with immediate, it is Rd, Rn and immediate, 8 Rd, Rn and immediate. So if we look into this, the opcode 10 bits, here will be 8 I for the opcode. This 12 bits is the immediate value, and we will need to convert this immediate value into hexadecimal or decimal value. We use the calculator in programming mode. Here is in binary mode, so we will paste the this bit sequence, the 12 bit sequence for immediate into this. We can see the value in hexadecimal, it is 243. In hexadecimal, in decimal. And here, from here you can see the next part of the next part is Rn. Rn value is 1111, so it is 31. And then this value, I think it should be 9, but we will check it right now. So this value for Rd is 9. So here is this one is immediate, this 31 it is RN, and 9 is RD. So now if we look into this, we know exactly how our instruction will be in assembly language. Like V8, it will be 8 I, and then value of RD here is 9, and in RD is 9, and register 9 will be written as X9 in rack V8, and so here it is X9 RN, it is 31, so it is X31, and the immediate value, that is 243. Well, so here we have our first instruction converted from binary into assembly code for rack V8, and we know that for the immediate value we will need a hash in front, so the instruction in rack V8 assembly code will look like this: 8i, X9, X31, and then hash 243. So up to here we already finished decoding the first 32 bits binary into understandable assembly code. Next, we will convert the second line or the second 32-bit sequence into assembly language. We can see here it is start by 0 0. Okay, let's take a space first. It start by 0 0, and then 3 1, and then 4 0, and then 1 0. So we try to look into this opcode to find the instruction. 2 0 and 3 1 is located around here. Here 2 0 and then 3 1s, and then 4 zeros here, and then 1 0. So it is this instruction LGURB. It is a D type, D format. So we know the opcode for this D type or D format will be 11 bits. So we cut it into 11. So here we have 11 bits, 2 0, 3 1s, and then 4 zeros, and then 1 and 0. The first part. And if we look into the D format, we know that D format has 11 bits opcode, 9 bits address, and then 2 bits that we want to use at this time, 5 bits for RN and 5 bits for RT. So we need to cut it into 11, 9, 2, 5, and 5. So here is 11. The next one will be 9. 9, 2, 5, and 5. And we know that this code is this opcode, say for this one LGURB. So here we have LGURB, and look at this, the address, 9 bit address. Here we know it is 0. 0 for address, and then these 2 bits are 0 in hexadecimal, and then this 5 bits Rn will be, if you look into here, it is 19 in hexadecimal, so 19, and it is Rn. The next one, the last one, Rd, that is this one, and its value in hexadecimal is 10. And it is RT. So we know the instruction here. It is LDUR LEDURB and then RT and then RN and address. So the correct instruction here, we will replace RT, RN and address by this value in hexadecimal. So the instruction will be LDURB and RT is 19. No, RT is 10, and so here the 10, the register 10, X10, and then RN 19, X 19, and the address 0, so hash and then 0. So here we have the instructions, assembly language for the assembly language instructions for this 32-bit sequence, and we know the meaning for this, that is loading the a value from memory shown by X19 into X10, as you can see it shown here. Next, we will go to the third instruction. So if we look into this, we can see it here double 1 and then double 0 and then 1 0 1 0. So we try to find it here. We can see here double 1 and then double 0 1 0 1 0, and then a number of 0 will be here. So it is an R type. It has 11 bits for opcodes, so 11 bits, double 1 0 double 1 double 0 1 0 1, and then a number of 0, so 11 bits. So it should be here for 11 bits. So for R type, we know that the next one is 5 bits RM, and then 6 bits that we want to use, and then 5 bits RN and 5 bits RD, and we know that this instruction is R type or exclusive OR. So this instruction will be OR, and look at this, we know that this 5-bit RM. The value of this RM is 9. And then these are a number of zeros that we want to take care of this time, and this Rn value is 10 in decimal, and it is Rn value, and finally the remaining 5 bits here will be 11. So here is 11, and it is RD. And so if we look into the instruction type of ER, RD, RN, and RM, we can say that our instruction will be this ER and then RD, which is 11. So the register is X11, and then RN, which is a 10, so it is a X10, and finally RM, which is X9. This one should be located here. So we have this is the exclusive OR between X9 and X10, and then the value will be written into X11. Next, we will go to the fourth instruction. You can see here it is 0, 0, and 3 1, and then a number of zeros here, and then finally 1 0. So we can check it here. You can see it here 0 0 3 1 3 ones, and then a number of zeros here. You can see it is a stub STURB, and it is a D format. It has 11 bits of opcodes, and so we will cut 11 bits here, and we know that this is the this instruction STURB here, and for the D format it is RT and then RT and then RN and address. Here, so we need to know where is the address, and RN, RT. Address takes 9 bits. So here will be address, and then RN and then 2 bits, and then RN and RT, each of them takes 5 bits. so the instruction should be cut like this. This is the opcode for STURB, and then the address here we can see it is number 0, and then this 2 bits we don't care about it, and this value in decimal, yeah, here you can see it here, so it is 19 in hexadecimal, 19 in hexadecimal, and it should be here. You might make reference here, you make reference to this format. It is RN, and then the last, this value you can see it here, so register number 11, and it is RT, here. So we will finally have the the instruction STURD RT will be 11, X11 for register number 11, and then RN register 19, X19, and then address we need hash before the value, and address offset address is 0. So this will be the instruction we have here. And so you can see this instruction means you store the value in register X11 to the memory at the offset address of 0. Well, next you can see that if we divide the code into group of 3 like this, you can see that the offset, the opcode of this instruction up to the bit 11 from the beginning, it is exactly the same with this instruction. The second one up to 10 bits. No, I'm sorry. Up to bit 11. It will be this instruction, and here for 11 bits here it will be this instruction. So you can see that these 3 lines will be represented by these 3 instruction, 3 opcodes, but of course you will have different in the address or in RM, RN, and RD. Similarly, for all other instruction, you can divide it by a group of 3, and you can apply the same with this opcode to find the assembly instruction, like exactly these 3, and you need to replace address RM, RN, and RD by yourself. Yeah, so we can divide it like this. Yeah, so we can see we can have a many group of 3, and each of those group will be add and then load from memory. Sorry, you will have a number of group of 3 instruction, load from memory, and then exclusive OR with some number, and then store it back into the memory. And if we do with all the instruction, we will find the code for this binary string for binary sequence like this. This will be the machine language, 32 bits each for one code, for one line of code, and the first instruction will be HI will be HI X9, and then X31 we will take care about it later, and then the number 243 Y X9 here, Y X31 here change to ZR. It will be explained here. If you look into this table for register name, and you can see that the register number 31, it will be XZR. It contains the 0 value, and it's specially used for value 0 only, and so it is XZR. And then it will be load from memory X10, X19, and offset address 0, and then exclusive for of X10, X9 here, and store into X11, and the fourth one will be store back. Sorry, here I have mistake in here. So here is store back from register X11 into memory with the base address at X19 and the offset of 0, and you can see you have a group of 3, and then another 3 load exclusive or store, load exclusive or store, and so on. But we use different memory location for loading data and store back, loading data and store back from offset address 0, 1, 2, 3, and so on until the offset address of 12. Now we will explain the code. We know that the add a value, an immediate value with 0 will return that value and store into X9. So we know that in X9 we will have an immediate value. For this code, we will load a data from memory, the first data in memory, into X10, and for OR it will be exclusive OR, and the exclusive OR will take X10 and X9 together, and X9 is this value together, and then store into X11, and after that X11 will be written back to the memory at the offset address of 0. So here load from address 0, and then exclusive OR with 243 and write into register, and finally store that value from that register back to address offset address 0. Similarly, we have the next 3 instructions. The next 3 instructions will do the same thing, but it loads from address 1 and then exclusive OR with this value 243 and store it into X11. Finally, that value will be stored back into the memory at offset address 1, and similarly we have all the value in memory from offset address 1 to offset address 12 will be loaded into register exclusive OR with 243 and then store back. We consider it from the viewpoint of encryption. We can think that here is a code written again with the comments here. We can consider that X9 will be the encryption key, that is 243, and from inside memory from offset address 0 to offset address 12 we have the data that we want to encrypt, and the encryption method is doing exclusive OR between the value inside the value in this memory together with the secret key or 243 here, and we will have a new number, and we can store, and we will store it back to the memory. And in cryptography, this method is known as a simple exclusive OR cipher, in which the input value x will be exclusive OR with a key, and so we have exclusive OR operation here, and the output of this operation of this exclusive OR operation, y will contain the encrypted value, and y equal x exclusive OR key. The operation exclusive OR here will be written by E or R in LAC V8 assembly language or LAC V8 instruction set architecture. And now we will go to our second part of our lab today, the part 2 about communicating with people. So the CGSD informs you that the following messages has been intercepted in the phone of the suspect. The message will be a number of a sequence of 0 and 1 bits like this, and the message received from outside will be another sequence of 0 and 1 like this. We assume that the code here, we assume that the message here will be sent and received by ASCII or American Standard Code. And so the question for you is, what information can you provide from this message sent and received? And so, in order to understand what is the sending and receive message, we will need to convert this binary sequence into ASCII code. So we will try to convert it now. So here will be the sending message. Well, they are the same, but in a different document. And this is the receiving message. And in our documents, you can also see here we provide the ASCII table for your reference. For ASCII table, of course, you can also find it by any search engine somewhere. You can do any search like this, and then you can find the ASCII table for your reference. We know that if we look into this, we can see it has if we look into the ASCII table, you can see it has the value from 0 to 127, and so the ASCII table will use 8 bits or 1 byte in there to decode, to encode the a character. For example, here you can see that the ASCII table, if the value is 32 in decimal, it will be the space character. If it is the value of 65, it will be a value in capital. And so we know that ASCII tables will use 8 bits each, so we need to divide the data into 8 bits. So here's the first 8 bit, the second 8 bit, the third, fourth, here, so you have a number of bits for the send and a number of bits for receive. Well, we will look into this calculator. We to check what is the value. Here you have the value of 10110010, which will be 178 in hexadecimal. And that value 178, we will write it here, 178. And if you look into our ASCII table, you can see that the biggest number in this table, it is 127. So this value 178 is not available in this ASCII table, and so we can expect that this message has been encrypted. We know that here we also have the code received from the same iPhone, and with our work we understand that that code try to encrypt a data from memory together with a key of 243, and so now we will try to decrypt this code using the same key by exclusive OR. This message byte, each byte together with the value of the key 243, and we will see what can we receive. So now we will try to, here it is a binary, and here is the decimal value, and we will have the key and exclusive OR. So now we take 178 and the key here is 243, and so we try to take this data 178. We have to change this from binary to decimal. So here it is 178, and we do exclusive OR together with 243, and we can see the value is 141. Sorry, and we can see that the value is 65 in decimal. So here it is 65 in decimal. And if we look again to our ASCII code, we try to find the 65, number 65 here. It is used to encode the character A in capital. So it is A. Here is ASCII code. Similarly, we have this value in binary will be 135 in hexadecimal. 35 in hexadecimal, and then we take that 135 and exclusive OR with here change exclusive OR with 243 and the region is 116. Oh, sorry, 243 for the key, and the exclusive origin is 116. And so if we look into the ASCII table for the value 116, it is here. We can see the corresponding character is T. In fact, I already do with all these data by exclusive OR, the send and the receive message byte by byte together with the key 246 to find the region, and I convert it into ASCII value, and it is written here. So here you can see that the message sent from somewhere will be decimal, and when you and the key we have in the previous code, that is 243, and if we make the exclusive OR between that message together with the key, you will have this value in hexadecimal, and when we make reference to this table, we can have the value of attack and then a space and then time, and that is the send message asking for the time of attack, and the received message say midnight. So here we have our final region. Our final result, you can see here. So the message sent converted to ASCII, that is attack time, and the message received, and which is converted to ASCII, it is midnight. Well, here we go to the end of our lab today, and if you have any questions, you can send me by your email. Thank you very much.